Good morning, everyone, and welcome to the Friday session. We will open the session today by the talk of Dr. Mantas Šimėnas. Mantas obtained his PhD degree at Vilnius University and then moved to University College of London, where he spent several years studying hybrid materials, employing electron spin resonance. At the moment, Mantas is already back at Vilnius University and continuing his research on hybrid materials, employing electron paramagnetic resonance. Today, he will present his work. The talk will last 45 minutes, and afterwards we will have some time for questions. If you have some questions, please raise your hand and you will have time to ask the question. Another request from my side, please mute yourself during the talk, that we have no additional sounds. And Mantas, please start your presentation.
Okay, thank you, Vytautai. Okay, I hope you can see the screen. Good. So first of all, again, thanks for the kind introduction. And also, I'd like to thank the organizers for inviting me to present my research in open readings. It's a great pleasure to open today's sessions. And before I move to the scientific part, I would like to say a couple of sentences regarding this very sad and terrible situation in Ukraine. So in case there is someone here who would like to listen for my talk, but supports this war, supports Putin, please leave. Frankly, I do not want you in my talk, and maybe spend this time to, turn on your critical thinking. And for others, I urge you to support Ukraine as much as possible. I'm sure everyone is doing this already. Okay, so moving from the sad topic to, let's say, more entertaining one, let's move to science. And today, I want to talk about hybrid materials. And as the title suggests, I will be talking about structural phases, structural phase transitions, and we'll touch some quantum effects in these materials. And this work was done in collaboration with many people, mainly with Jūras Banys lab here at Vilnius University, also colleagues from abroad. So the outline of my talk, first I will introduce you to the hybrid materials, then the methods we use in our lab to study these materials. Then I'll talk about mixed methyl ammonium based hybrid perovskites, then about rotor dynamics and some metal organic framework, and finally I will conclude with describing our recent discovery of methyl group tunneling in another hybrid material. Okay, so what are these hybrid materials? These are crystalline materials that have metal centers and some organic parts. And the most popular hybrid materials are hybrid perovskites. And perovskite, you can imagine this is just or the topology, structural topology of a crystal, and the best example of a perovskite inorganic example, classical example, would be barium titanate, which consists of titanium oxide octahedra that are joined in such a manner, and inside there is a void for another cation. In this case, it's barium. And recently, lots of scientific attention was concentrated on exchanging some of the inorganic parts in perovskites by organic motifs. And in such a way, such structures were formed, and this is methyl ammonium lead halide perovskite, where you can see now that in this void in the center we have organic molecular cation, so organic motif. And there could be actually different hybrid perovskites depending on the bridge which joins these octahedra. So there could be halides, but there could be organic linkers like formates, for example, and so on. All the examples are shown here, and one can get very fancy big structures like this one, for example, here with this huge molecular cation in the center. And due to high variety of different metal centers and organic parts, one can get different properties, of course. And these properties can satisfy everyone's taste. They range from photovoltaics, so halide perovskites here, the leaders, then some of them are ferroelectrics, multiferroics, ferromagnetics, and so on. A broader class of hybrid materials is metal organic frameworks, or MOFs for short. And these materials are similar to perovskites, but they can have basically any structural topology. And these compounds consist of, again, metal centers coordinated by some organic motifs. And these metal centers are connected by organic linkers into such porous structures. And there could be huge variety of different structures. So thousands different MOFs are known already. And the common property of these materials is that all of them, they have high porosity. So these yellow spheres here, they show the porosity of the materials. This porosity could be, of course, utilized for different applications and mainly related to gas absorption and gas separation. So, for example, one can capture CO2 from the atmosphere using metal organic frameworks. And the hybrid materials we study in our lab are shown here. So we mostly concentrated on formates, where we have formate linker joining the octahedra, and then inside we have this molecular cation. We also study halides, methyl ammonium based mainly, and we also study different MOFs. And during, let's say, last 6 years, we published quite many studies on these systems. And today I'm going to present our recent results, which we published in quite good journals. So before I move to the results, I also want to tell you about structural phase transitions. So probably you know, well, I'm sure you know ordinary phase transitions, such as, let's say, freezing of water, right? But there are other phase transitions that are called structural, and those occur basically in every crystal. And these transitions happen when external stimulus is changed, for example, temperature or pressure. And a good example would be, again, going back to classical inorganic system, barium titanate. So when the temperature is lowered, this barium in the center is shifting from the, let's say, equilibrium position. And this shifting, of course, happens in the whole crystal. And because of that, crystal symmetry changes. And this is also accompanied by appearance of spontaneous appearance of useful physical properties, such as, for example, electric polarization. And then this material becomes so-called ferroelectric. And phase transitions, they show anomalies in thermodynamic variables, for example, heat capacity or dielectric constant, as shown here for barium titanate. So we have the phase transition points, this anomalous behavior. So we'll see that we see similar effects in hybrid compounds as well. And the methods we use in our lab are shown here. So mostly we are concentrated on broadband dielectric spectroscopy and EPR spectroscopy. So broadband dielectric spectroscopy means that we can measure dielectric properties from millihertz frequencies to terahertz, so many orders of magnitude in frequency. Of course, covering all the frequencies requires different experimental techniques, but I won't go into the detail of these techniques here. I think it's too detailed. And as I said, we also use EPR, so the spectrometer of electron paramagnetic resonance is shown here. I'll give you more details about this technique a bit later. We also use other techniques such as electric polarization measurements, ultrasound propagation experiments, vibrational spectroscopy. We also do some theory to back up our results. And one slide about principle of the dielectric spectroscopy. So using dielectric spectroscopy, one can measure dielectric response or complex dielectric permittivity. What does complex mean? Well, it means that the real part is just ordinary dielectric permittivity or dielectric constant, if you wish. And the imaginary part of this quantity corresponds to dielectric losses. And probably you know very well dielectric losses if you are using microwave ovens. So there are huge microwave losses of water at gigahertz frequencies, and this is used to heat up the samples, not the samples, the food, of course, in microwave ovens. And in my talk, I will be concentrated on this lower frequency range, where we can study motion of electric dipoles using dielectric spectroscopy and some, let's say, charge separation effects. And we'll be looking mainly at increase of the dielectric losses in the spectrum. And this increase corresponds to a frequency which is related to characteristic motion of electric dipoles. So we'll be studying motion of, or let's say rotation of electric dipoles. And from dielectric spectroscopy, we can determine the relaxation time or characteristic dynamic scale of electric dipoles. Then we can also determine the activation energy if we do temperature dependent studies. And we can also look for phase transitions and some peculiar exotic phases such as glass of electric dipoles. Okay, let's move to the results. So part one, so where I'll be talking about molecular cation mixing in methyl ammonium lead bromide hybrid perovskites. So pure methyl ammonium lead bromide, its structure is shown here. So it consists of lead bromide octahedra, and in the center we have methyl ammonium cation. Now this compound has 3 structural phase transitions. So this is the phase diagram, and during these phase transitions, the methyl ammonium cation, and once the temperature is lowered, becomes ordered. So if we start the cubic phase, let's say at room temperature, the cation can move randomly, so it's stochastically rotating. But then when we decrease the temperature in the orthorhombic phase, the cation is not moving anymore, and all the cations are ordered, meaning that there is long range order in the system. And recently, there was a huge interest in trying to mix or swap this methyl ammonium with different cations. So for example, formamidinium. And this was motivated because these materials are used in solar cell fabrication. And when you swap, when you mix the molecular cations, one can see that the efficiency of the solar cells increases substantially. And this was as shown here over the year. But despite many studies studying this, let's say, efficiency of solar cells in the mixed compound, the mechanism behind the mixing or its effect on the structural phases was still unknown. And what we expected was that if we mix, then we can introduce frustration in our dipole system. And you can understand frustration. So let's say if one dipole is pointing up, another is pointing down, then the third dipole doesn't know what to do. So it can either point up or down, so the system becomes frustrated. And frustration leads to exotic phases, such as dipolar glass, as is shown for classical inorganic systems. And bipolar glass is can be well studied using dielectric spectroscopy, and it appears as very broad anomalies in the temperature dependence of the imaginary and real part of the dielectric response. Okay, so first we wanted to mix methyl ammonium lead bromide with dimethyl ammonium lead bromide, which due to big size of dimethyl ammonium cannot form perovskite structure. So pure dimethyl ammonium lead bromide is hexagonal, and because there is clear incompatibility between these two structures, one can expect that there is a solubility limit, how much dimethyl ammonium one can put in this structure. And the limit is roughly 30%. It was determined by previous studies. So we wanted to investigate concentration ranges up to 30%. And we had samples with 0, 4, 14, and 21% of dimethyl ammonium. And first, we performed differential scanning calorimetry experiments that basically show the method is used to show the phase transitions. And for the pure compound, we obtained 3 phase transitions, 3 anomalies, everything is understandable here, nothing new. For 4% of mixing with dimethyl ammonium, we saw shifting of the phase transitions to lower temperatures. And this shifting indicates that we stabilize the cubic phase. And for even higher concentrations, for 14 and 21%, we saw no phase transitions. And the system remained in the cubic phase. So we completely suppressed the phase transitions by mixing. And this suppression occurs, of course, because we disrupt significantly the lattice, we disrupt the ordering of methyl ammonium cations by introducing this bigger dimethyl ammonium cation. Our results were also supported by single crystal X-ray diffraction, where again we saw only cubic symmetry for these higher concentrations. And after that, we decided to measure broadband dielectric response to check maybe we have frustrated electric dipoles, or maybe we have indications of dipolar glass phase. And of course, since methyl ammonium has big electric dipole, in the dielectric response, we saw mainly effect from this cation. And here you can see real and imaginary part of the electric permittivity versus temperature for the pure compound, non-mixed one. And here the main point is that we have at the phase transition from the tetragonal to orthorhombic phase, we have sudden drop in the dielectric permittivity, and this drop is related to the ordering of these cations during this phase transition. So the system becomes completely ordered. It is no longer susceptible to external electric field. With 4% of mixing, we saw the same transition, but it became broader, as was expected also from differential scanning calorimetry experiments. And situation changed drastically for 14 and 21% of samples, whereas that of the phase transition, we saw very broad anomalies, also in the frequency domain, which is not shown here. And these broad anomalies indicate that indeed we have frustration and signatures of dipolar glass phase. From the dielectric spectrum, we were able to determine the relaxation time of methyl ammonium cation motion, which we can plot in Arrhenius coordinates and get the activation energies. Basically the barrier of motion for methyl ammonium, and we obtained that this barrier increases almost 2 times when we increase the concentration of dimethyl ammonium, and this means that this guest cation hinders motion of methyl ammonium. Our results were also supported by DFT calculations performed by Aaron Walsh group at Imperial College London. So there they used this supercell containing 8 molecular cations with periodic boundary conditions, where one cation, one methyl ammonium, was replaced by dimethyl ammonium. And what they observed was that this dimethyl ammonium significantly locally perturbs the lattice, deforms it, and that this deformation dies out with the distance from dimethyl ammonium. So it locally affects motion of methyl ammonium cations. The next system we investigated was mixing with formamidinium cations. So formamidinium lead bromides can form a perovskite phase, meaning that then these two structures are much better compatible. As you remember, for dimethyl ammonium, we had no perovskite phase. So in this case, we can expect no solubility limit. So we can get any concentration we want. And we investigated the whole range of concentrations. So first we did heat capacity experiments, and these are the concentrations we studied. And what we saw as we go from, let's say, non-mixed compositions, which are shown here at the top and at the bottom, we see that the phase transitions, they are shifting to lower temperature, but the phase transition anomalies still remain. They become broader, but they are still there. So there is no full stabilization of the cubic phase. The phase transitions still remain. And this was also observed in the dielectric response. Here one can see the dielectric permittivity for 20% of sample, and we still have anomalies of the phase transitions. With the 50%, everything is much broader, but we still have anomalies. And at 80%, we are continuously switching to formamidinium, pure formamidinium case. And we start seeing phase transitions from that compound. And from the dielectric response, we managed again to obtain the rotation barrier for methyl ammonium cation. So here you can see this rotation barrier versus formamidinium content in our mixed system. And what we saw again, that this barrier increases with the level of mixing, which makes sense because again, these additional cations, these guest cations, they influence, they hinder the motion of methyl ammonium. Here you can also see the phase diagram, which we're able to determine using these different concentrations. And the main point here is again that the phase transitions are not fully suppressed even for the highest mixing level. And this means that, of course, methyl ammonium and formamidinium, mixing of these two is much more compatible than mixing with dimethyl ammonium. And this concludes my first part. So again, the whole message would be that mixing suppresses phase transitions. And this is, of course, useful because if you have a phase transition around room temperature, let's say, and if you want to use these mixed compounds as in solar cells, you do not want phase transitions, right? You do not want phase transition happening when you change temperature of your solar cell. And the second conclusion would be that formation, this glass phase, dipolar glass phase, requires substantial deformation of the lattice or cation size mismatch, as was observed for dimethyl ammonium case. Right, let me move then to second part of my talk, which involves investigation of different system, mainly MIL-50 free aluminum-based metal organic framework. and we wanted to study some molecular rotters in the system. So this compound, again, it's a hybrid compound, so it consists of metal centers, in this case aluminum, and these centers are connected together by terephthalate linkers into such porous structures. And the idea was, these structures are well known, but the idea was to try to functionalize this linker by some chemical groups and see how the structure changes and how this functionalization affects dynamics of these linkers, because we expect that these linkers tend to rotate around their symmetry axis. So what happens when we disrupt the symmetry? First, we did X-ray diffraction experiments of unfunctionalized MOF, and we obtained the system as expected in this large pore phase. So the diameter of this pore is roughly 1 nanometer. Then we also measured nitro functionalized MOF, and again we observed this large pore phase. So not huge difference in terms of structure, but a huge difference we observed for amino functionalized metal organic framework. And in this case, due to stronger interactions between the groups and the linkers, we get a narrow pore phase. So the pore diameter is roughly two times smaller in this case. And this will be important, as you'll see in the next slide. So then we switched to dielectric spectroscopy because we wanted to study dynamics of these linkers. And of course, in unfunctionalized system, we did not observe anything, so very small signals. And this makes sense because the non-functionalized linker has no electric dipole moment. So we see no dielectric response. But we see nice dielectric response in nitro-functionalized linker, because then we break the symmetry and this linker gains electric dipole moment. And we managed to obtain that this linker rotates around this, let's say, a longer axis. And this was also in agreement with NMR results. I'm not showing here, but basically dielectric spectroscopy was able to characterize this motion. And we also did not see anything in amino functionalized MOF. And the reason why we did not see anything is that in this narrow pore phase, the linkers are not allowed to move. So they are pressed, and due to steric repulsions, there is no substantial motion. Then our colleagues who actually initiated the study, they performed ab initio molecular dynamic simulations which can probe motion of these linkers. And what they observed was that this motion is coupled. Maybe I can show you a video. Can I show it? Okay. So as you can see, let's concentrate our attention on this center linker and the one on the left. So as one rotates, it's actually is pushing another one. So this motion becomes coupled. So one linker is affecting another one. And this was the main conclusion of this project. So we were able to observe these coupled molecular rotters in a MOF for the first time. And this results in gear-like functional motion in metal organic frameworks, especially if in the future we could control these linker dynamics by, for example, application of some electric field. We could make, let's say, a basis for a nanorobot. Okay, this I'd like to move to the last part of my talk, which is about methyl group tunneling in dimethyl ammonium zinc formate hybrid perovskite. And to study this system, we used EPR spectroscopy. So let me briefly introduce you to EPR in a nutshell. So EPR spectroscopy is used to probe electron spins. And probably most of you know that electron is a quantum particle. It has spin 1.5. And spin you can imagine as a tiny quantum compass needle that can have only 2 states. So if we apply magnetic field, let's say it's pointing up, so then the spin could either point up or could point down. So we have 2 states, and the energies of these 2 states for a free electron are shown here versus magnetic field. So when we increase the magnetic field, the separation between these 2 states increases. And of course, this forms a basis for spectroscopy, because then we can use some electromagnetic signals to induce jumps between these 2 levels, so we can flip the spin. And this is typically done using microwaves at gigahertz frequencies, just because they're convenient in the lab approachable fields. This splitting corresponds to microwaves. And then if we sweep the magnetic field and irradiate microwaves at a constant frequency, so our quantum has the constant energy, then at some point the magnetic field will get the absorption of microwaves, so we'll get EPR signal. The situation can get much more complicated if we have not a free electron, but something like manganese 2+ ion, which has 5 unpaired electrons, and so this total electron spin is 5 halves instead of 1/2. And in addition, we can have nuclear spin. In this case, it's also 5 halves. So this results in many levels. And of course, then the EPR spectrum becomes much more complicated, but on the other hand, much more informative. So we can gain a lot of information if we can manage to tackle the spectrum. And in addition to this continuous or so-called continuous wave irradiation of microwaves into our system, we can also use pulsed techniques where we employ nanosecond length microwave pulses to excite and read and manipulate our spin system. And a little bit about one of these pulse techniques, which is called electron spin echo envelope modulation, or ESEEM, because this technique I will be using to investigate the hybrid material. So in this technique, we are using 3 pulses, again, short microwave pulses. And the main point here is that this technique, we can probe weak interactions between our paramagnetic center, so our unpaired electron, and some distant nucleus, so for example a proton. These interactions are very small. They are called hyperfine or super hyperfine interactions, and these pulse methods can be used to determine these interactions. Of course, when we determine these interactions, we can this tells us information about local structure around this paramagnetic center. So basically the shape of the wave function of this unpaired electron spin. And what we expect if we do this ESEEM experiment, so we expect some splitting in our spectrum, which corresponds to this weak interaction. And we also expect, when we perform this experiment at different fields, we expect the shifting of our signal to higher frequencies at higher fields. So the frequency of this signal, the center, is proportional to the magnetic field. Okay, after introduction to EPR, let's go back to the system, and let me tell you a couple of sentences about dimethylammonium zinc formate. So it consists of zinc oxygen octahedra that are joined together by these formate linkers into, again, a perovskite topology. And in the center, now we have dimethylammonium cation. So as you remember, for lead halide perovskites, we were not able to accommodate dimethylammonium in the center because it has bigger size. But in this case, because the linker is much longer, so there's much more space, and dimethyl ammonium fits. Now, this compound has a structural phase transition at 160 K. And above this temperature, what is happening is that this cation can hop between 3 positions. So it's constantly moving. All the cations, of course, and the crystal are constantly moving, and they are moving between 3 positions, which is a random rotation around this symmetry axis. And when we cool down below 160 K, all these cations become ordered, and the long-range dipole order is established. And we wanted to use EPR to study this phase transition initially, and of course there is a problem because zinc 2+, which is sitting here, is diamagnetic. So the whole system is diamagnetic, meaning that all the electron spins are paired up. So typically they come in pairs, and then the total electron spin, the net electron spin is 0. It's cancelled, so we cannot do EPR on the system. But we asked our chemists to introduce a little bit of manganese 2+ in the system during the synthesis. And as I showed before, manganese 2+ is paramagnetic. So we have EPR active probe in our system. And here you can see continuous wave EPR spectra of this compound recorded at different temperatures. So here at the bottom is this the same plot as above, but just zoomed in the outer parts of the spectrum. And here the main point, I won't be explaining, this is of course manganese signal, all these lines, this is too complicated, but the main point here is that when we change the temperature and cross the phase transition point, we see a drastic change in the EPR spectrum, as can be seen, for example, comparing these two curves. And this means that our manganese is, of course, susceptible to the phase transition. That's good news. That's what we wanted to investigate first. And then we can simulate the spectra and plot the parameters of this paramagnetic center versus temperature, and obtain information about the phase transition. We obtained strong first order phase transition, and this was in agreement with our Monte Carlo simulation, so everything was fine. Until we switched to pulsed EPR experiments, where we use again short microwave pulses. So we wanted to do 3-pulse ESEEM experiment, as I showed before in this system. And again, this is what we expect. We expect a shift of frequency of our signal with increasing magnetic field. And these are our experimental results. So what we observed was that the line did not shift when we changed the magnetic field. And this was really interesting. So this result I obtained during my last years of PhD, and I always tell this, which is a true story. So my supervisor, Professor Jūras Banys, was really concerned. He said that, well, this experiment broke his understanding of physics. And so it took us a while to understand what is really happening here. So first thing we did, we measured the temperature dependence of the signal. And what we observed was that the signal decays as the temperature is increased above, let's say, 50 K. And also from this data, we can obtain some activation energy of this process. And that activation energy was close to methyl group rotational activation energy. So this was our, let's say, suspect number 1. And to investigate this, what we did, we changed protons in this framework and on the molecular cation by deuterium. So we selectively changed some of the protons, and here you can see the formula of of this compound, where in some cases we have, instead of protons, we have deuteriums. And this signal completely disappeared when we changed protons of methyl groups by deuteriums. And this proved then that, okay, this effect is really related to methyl groups. And we thought about this for quite a bit, and the conclusion was that actually using EPR spectroscopy, we can observe tunneling, quantum tunneling of methyl groups. So just a reminder of the quantum tunneling effect. So if we have, let's say, a quantum particle, a quantum system, which is described by some wave function, and if we have a barrier which has higher energy than the quantum particle, then there is a finite probability that the particle could actually appear on the other side of the barrier, so that it can tunnel. That's the term describing this phenomenon. And with the methyl groups, what is happening? So at high temperature, they are just randomly rotating classically, but when we cool down, the rotation barrier becomes higher than the thermal energy, and of course they cannot rotate classically. They become quantum rotors with some probability of quantum tunneling. So there is a probability that a methyl group can, let's say, vaguely can rotate even if the barrier is higher. And the main point is here was that with EPR spectroscopy, we can excite manganese center, and this manganese center interacts via hyperfine interactions, via these small interactions with the protons of methyl group, and this allows us to read out the tunneling by microwaves using this manganese center as the intermediate step. We were able to simulate the obtained ESEEM spectrum, this tunneling spectrum, using some, let's say, density functional theory, and we were able to obtain the frequency, the tunneling frequency, which is basically just the splitting of the two tunnel states. And from this frequency, the main point is that we can get the rotation barrier of methyl group tunneling, and that was around 10 kilojoules per mole. And we also did DFT calculations of this rotation, and it predicted a very similar number, which again proved our hypothesis. So to conclude the last part, I'd like to say that this methyl group tunneling is very sensitive probe, because the frequency of the signal highly depends on this rotation barrier. And because of this, one can imagine that if one can detect this methyl group in other systems, so for example in proteins, one can have a very sensitive tool to study local methyl group environment, which is of course let's say very useful, especially in proteins if you want to determine some packing of the proteins. And hopefully this could lead their expectations to a new type of EPR spectroscopy. So EPR spectroscopy is characterized in different sub-spectroscopies, and this could be one of them, hopefully. Okay, with this I would like to conclude my talk. The main take-home message is that hybrid materials are fun. So they form a playground for different studies, and they have different properties, and I'm sure every physicist or almost every physicist or chemist could find an interesting system to study. This I would like to thank people involved in this work. So group from Jūras Banys and especially Sergejus Balčiūnas, who did dielectric experiments. Then huge thanks for Miroslav Mączka from Polish Academy of Sciences, and his group who synthesized the hybrid perovskite samples studied here. So really, he's a brilliant chemist. If I want a system, I just have to ask him, that's it. Then EPR part was done in collaboration with Andreas Popol and Gunnar Jeschke, so from Leipzig University and ETH Zurich. And DFT was done by Aaron Walsh from Imperial College London and Kęstutis Aidas from Vilnius University. And the rotor dynamics was studied together with Monique from Technical University of Delft. Okay, thank you for your attention. I'm open for questions.
Mantas, thank you very much for your interesting presentation, and I see that you've made a substantial input to the field of science, and now you were perfect in time, and we have some time for discussion. So if someone has a question, please raise your hand. I see no hands, so I have some questions. So starting, the first question would be about EPR spectroscopy. So the materials you initially study is EPR blind, and you dope it, in this case, with the manganese, and then observe this tunneling effect using EPR spectroscopy. Have you tried to use other EPR active dopants, and have you observed similar effects?
Yes, that's actually, so I just got a project from Lithuanian Research Council to investigate this effect using different paramagnetic centers. And we have good candidates for this. So we have cobalt system. So instead of manganese, we have cobalt 2+, we have nickel 2+, and in all these systems, we observe similar effects. And the main point is that, of course, when you dope it, the lattice become, you distort the lattice locally, right? Because this you change zinc with another ion. And peculiar thing, what we observed with these cobalt and nickel systems, the results, of course, are still preliminary, but we think that we see a shift in the tunneling frequency, and this already indicates that this local doping affects the rotation barrier of the methyl group. So we can basically study this deformation of the lattice when using different dopants.
And so different dopants have different radii. How sensitive is the system to the difference of the dopants? Have you performed some preliminary research on the crystal structure, how it changes when you use different dopants?
Yeah, so the thing is that we are using something like significantly less than 1% of dopants, and because of this we cannot use ordinary structural X-ray diffraction methods to study the structure, because of course this signal is lost in the signal of the main compound. And then the idea is precisely to use EPR to study the local environment of these paramagnetic centers, and also to study the effect of these paramagnetic centers on the tunneling, which can then tell us the rotation barrier, how it changes, so which is of course related to the deformation.
Any more questions? Okay, so I have one more question for you. We still have some time for discussion. At the beginning of your presentation, you've shown the variety of perovskite structures, from very compact barium titanate based to very large dicyanometallate paste.
Yeah.
Can you comment on the stability of the perovskites while changing their structure? Because from my point of view, the first one, the very compact one, seems stable, while increasing the structure seems to be less stable.
So let me share maybe screen, it will be a bit easier. Okay, so you have these perovskites here, right? And the stability, if we take, let's say if we start from formates and go to this side, the stability, of course, decreases when this becomes longer. So this is less stable. But if we look at the halides, for example, where the octahedra are joined by a halide, these compounds are not stable. And that's actually a problem for, even though these are small, right? But they are not stable. And this is a problem for using them in solar cell applications because they react with water and the air and so on. And these compounds are not that stable. So for example, formates are much more stable than halides, even though there's a bigger cation inside and the structure is bigger overall.
Okay, thank you. So we still have time for one question. Okay, I see no more questions. So Mantas, thank you very much for your very interesting and very informative presentation. I wish you success.
Thank you.
Bye-bye.